So remember, when working with our cubic equations of state, we can get up to 3 real roots. Okay, so if we get 3 real roots, the largest root will correspond to vapor phase, the lowest root will correspond to liquid phase, and the middle root will throw out. Okay? And so if you encounter this scenario, it's important to know what your phase is so you can select the appropriate root. So especially in the quiz I make you take in class, what I ask you to use is what I call the simple vapor pressure equation. And so the simple vapor pressure equation is given here on the Canvas page. Okay? So this is a simple equation to estimate the vapor pressure of a fluid if you know the critical pressure, the critical temperature, the eccentric factor, and then your temperature of pressure of interest. Okay? These are all variables that you would need to calculate molar volume using your SRK or Pang-Robinson equation of state. So if you have all that information to do an SRK or Pang-Robinson calculation, you have the same information here that you can use to estimate vapor pressure. With that estimate of vapor pressure, you can use that to determine what phase you are to select the appropriate root, right? So if your pressure is greater than your saturation pressure at a given temperature, then you're liquid. If your pressure is less than your saturation pressure at a given temperature, then you're vapor. Okay, and so what I just want to show you is, well, I showed you some MATLAB code to perform the calculations as SRK and Pang-Robinson. There still seemed to be some confusion about just using this simple expression. And so what I wanted to show you is MATLAB code I created to do the calculations for you, and then a script that'll demonstrate applying these equations based on our example 2.11 that we used to test out my code for cubic equations of state. So this is just a function. Okay, so it's going to do the simple vapor pressure calculation. So it's going to have inputs of eccentric factor omega, temperature in Kelvin, critical temperature in Kelvin, and critical pressure in bars. And it's going to return back the vapor pressure, saturation pressure in bar. And so it just goes through the equation that it just had up. It just break it up into small steps. And then what I provided you with is this script, ethylene simple vapor pressure. And it's just based off of example 2.1. So in example 2.11, we used van der Waals, SRK, and Pang-Robinson to estimate the saturated liquid and vapor volume of ethylene at 260 Kelvin. And in the problem, we were told that the saturation pressure is 30.35. And so all I did is I copied that script and modified it, where I kept our critical properties and eccentric factor for ethylene unchanged. Temperature, I keep up there. Okay. Actually, I forgot to delete the pressure. Let me delete it there. And what I'm going to do is use our simple vapor pressure equation to estimate the vapor pressure, where again we were told the experimental value is 30.35. And so all I'm going to do is I'm assigned to PSAP bar the result of calling my function simple vapor pressure, in which I pass omega, temperature in Kelvin, critical temperature in Kelvin, and critical pressure in bars. Okay. And so if I were to run this, ethylene, simple vapor pressure, right, I get 30.5238, which is pretty close to that reference value of 30.35. Okay, so the only purpose of this video is to show you, a function that I'm sharing with you to perform these simple vapor pressure calculations, and then this ethylene simple VP is just a script which demonstrates how to call and run the function, and using our variables from that example 2.11 that we use to demonstrate our equation of state code.